So we've learned, you've been introduced, let me say, you've been introduced to the material for writing chemical formulas and structure of the periodic table. Now what we're going to do is take those chemical formulas and put them into, those are the words. That's the alphabet. We learned the words. Now we're going to put them in sentences, which is balanced chemical equations. See if I can do this. There we go. So we've got several concepts that need to be nailed down, and then learn how to balance equations. If you read through your textbook, chapter 6, more than likely it'll give you a couple of hints maybe, but won't really tell you much as to how to balance equations. It just tells you the end result, what needs to be at the end. But I'm going to give you a way to balance equations that's fairly reliable. Okay, first things first. Once we have the formulas written, like this SNF2, what is that? Right, we learn how to name compounds. Don't remember. All right, what's SN? Hint, it's Latin. Stannum, which is 10. If that's the formula, then how do you name it? Right? Is it a type 1 or a type 2? Can't be a type 3 because there's a metal, non-metal, right? Everybody nod. Okay, good. So you have to say what the charge is. So what's the charge on 10? Fluorine is a halogen, so it's always -1. So that means this has to be a +2. So 10,2 fluoride is the name of that compound. If you're given a problem where you are told that 10,2 fluoride reacts with something else, then if you can't write that, then you will never be able to balance an equation. That's why we learn how to name compounds first. Okay, so let's pick it up from there. What we will need to be able to do at some point is to say, how much does that formula mass weigh? What's the mass of that formula? And we know how to read the mass of each individual element. Just take it right off the table, right off the periodic chart. If you want to know the mass of the formula, you just say, how much is 10 worth? Well, it's 118.71 atomic mass units. How much is fluorine worth? 19 to 2 decimal points. But you've got 2 of them, so you have to multiply it by 2. And then you just add them all together. And that's the mass of that unit. 156.71 atomic mass units. Now, you probably, I hope you're wondering, what can we do with atomic mass units? And the answer is virtually nothing. Not in the lab. Because there's nothing in the lab that measures things in atomic mass units. Right? So I'm going to make a transition here in a second that makes those values useful in the laboratory setting. But before we do, let's take this example. H2SO4. Anybody recognize that one? Starts with a hydrogen, so if it's in solution, if it's in aqueous solution, it's what? It's an acid, right? Starts with a hydrogen. In this case, it starts with 2 hydrogens, right? So how do you name an acid? If it's got oxygen, do you start with hydro? No. If there's an oxygen in that molecule, you don't start with hydro. You take this part of the molecule and say, what is that? Right? It's a polyatomic. So you look it up in that chart I gave you. Sulfate, right? It has 2 hydrogens. So the sulfate is the root of the name. And H become X. So this would be sulfuric acid. And that, technically speaking, that's if it's in solution. Okay, so the sulfuric acid, what's its formula mass? Right, you got 2 hydrogens, right? That's 2 hydrogens plus sulfur. What's sulfur? Right, we have to look it up. I can't see that far, so I got one over here. Sulfur, 3207. And what are our units as of now? Atomic mass units, right? And then what else? 4 oxygens. So how much is an oxygen? To 2 decimal places. 16. So you add all those up, right? 2.02 and 64 and 3207, just add them up, and you should get 98 atomic mass units. Probably, that's rounded off, obviously. Okay, so we need some way to make those atomic mass units useful. And as it turns out, when you have the atomic mass unit value for a formula, you also can say that that is that many grams per mole of those units. Now we're going to define what's a mole, right? It's not a little furry creature that digs up holes in your yard. Right? A mole, in chemical terms, is a number of things, right? And it turns out to be 6.022 times 10 to the 23rd things. It could be atoms, it could be ions of an element, or it could be so many units, right? And in this case, it's a mole of these units, that formula. So that many of this unit will weigh that much, 98 grams. Okay? Now, how do we arrive at that? Well, we needed a standard, something that we can fix as a certain mass per mole. And it's bounced around over the years. At one time, we used oxygen isotope 16. We used that one as our standard. That was a little more difficult to deal with because oxygen's a gas and it usually occurs as 2 of them, right? So that just complicates things too much. There were reasons for entertaining the idea of using that, but they don't matter to us. Eventually, IUPAC settled on carbon-12, the isotope of carbon that has 12 nucleons, 6 protons, 6 neutrons in its nucleus. That particular isotope. Oh, what's IUPAC? I didn't tell you that, did I? That's the International Union of Pure and Applied Chemistry. There's also one for physics, Pure and Applied, PAP, physics. But this is the one that controls standards, naming conventions, the rules that we use to name compounds. Those are the people. or a subcommittee of that group decided what the rules would be. Okay, so back to carbon. This standard, this carbon, if we have isolated carbon-12 isotopes in a unit, and we have this many of them, 1 mole, then they will weigh exactly grams. So that exact number is applied to only that isotope. 12 grams for a mole of those. And everything else is referenced to that one. That's basically what that slide says. Now, there are actually, this value is experimentally determined. I gave it to you in terms that it sounded like we knew this first and then we did that. But actually, we decide this and then we decide how many that is. Right? But that's for people that do that for a living. Right? All we need to know is what's that value and what does it mean in terms of carbon. And then we reference everything else to carbon. So that's why all other isotopes, no matter what they are, will never be infinite zeros. Only carbon has 12 point infinite zeros grams per mole. The rest of them are fractions. They may go out here ways before you get one, but they're all fractions, decimals. Okay, so now we've got our reference. We can determine the mass of a mole of any element on the table. Once that's been determined, then it's a simple calculation to do formulas. Okay? Now, the other problem is, right, there's always a problem, is that chemists don't work in the lab with isotopes. They work with naturally occurring mixtures of isotopes. Right? So in nature, this carbon is going to be like, I don't know, 98% or more. And then you'll have maybe a 13 would be a smaller fraction. So the value that's reported in the table is a weighted average. Right? It'll be very close to 12. But it won't be exactly 12 because you got a few of these that are kind of weighting it toward the heavy side. So if you round it off to 2 places, naturally occurring carbon with no isotope, no A number up here, will be 12.01 grams per mole. So those are the numbers that you see on the periodic table, the weighted average for a naturally occurring mix of the isotopes of whatever element. Most of them will be very close to a whole number with just a small fraction out here. A few of them, like chlorine, will be, well, chlorine is 35-45. So it's almost split evenly between Cl35 and Cl36. That's why it's almost in the middle, the weighted average. Okay, I spent enough time on that right now. Let's learn how to use this information. Okay, like I said, once the value of that mole has been determined experimentally, it's just a number, right? It may fluctuate a little bit over time as people that are obsessive about that, or their job title says they have to be, they will refine that number. But for our purposes, 6.022 will never change. So that, as far as we're concerned, it's just a number of things, right? In this case, eggs, right? I would have said chickens, but eggs is okay. or molecules or atoms or ions, doesn't matter. It's just a number of things. So if we say how many eggs does 1 mole of egg contain, 6.02 times 10 to the 23rd eggs. They lopped off the last two. I like 022. Okay. So what I was describing as grams per mole is called molar mass. Or sometimes old school, you might see me slip and call it molecular weight. I can't help myself. But I mean molar mass. How much does a mole of that something weigh? What is its mass? And the molar mass of, let's see, the molar mass of nitrogen is 14.01 grams per mole. And if you add up a carbon and 2 oxygens, you get 44.01 grams per mole for carbon dioxide. Okay. All right. Oh, and notice that if you have a ratio like that, grams per mole, that can be used as a conversion factor. Right? Suppose you have so many moles of nitrogen. I give 2 moles of nitrogen. And you want to find out what mass is that. Dimensional analysis says we put moles on the bottom, right, to cancel moles here in the numerator. And then grams on the top. So we could put 14.01 grams per mole. Moles cancel. 2 times 14.01 is about 28 grams. So 2 moles of nitrogen weighs 28 grams. Okay. So these are all can be used as conversion factors. Okay, what's the mass in grams of 2.5 mole sample of ethane? Let's see, are they going to force me to do it? Oh no, there's the calculation. 2.5 moles, let's see, give my pointer right there. 2.5 moles of ethane. You find out, all right, how much is 1 mole of ethane? Well, there it is. We just say 2 carbons and 6 hydrogens, add them together. And that's the value you get. And that's 1 mole of that formula. So you can cancel the moles and leave you with grams. So 2.5 moles of ethane has a mass of 75 grams. Okay? You're going to need to know how to do this when we get to using balanced equations for stoichiometry. That is, how much mass of reactants goes in, how much mass of products do you expect to come out? You got to be able to do these conversions in order to make that work. Okay. So I encourage you not, if it's going in one ear and out the other, then plug up the ear that it's coming out. Hold it in there. And you can work backwards. Say if you have 50 grams of water and you want to find out how many moles of water that is. Notice that with any conversion factor, what is a conversion factor equal to? All conversion factors. 1, exactly. So that means if you've got this value on top of this value, that's the whole thing's equal to 1. Just flip them. It's still equal to 1. Right? Okay. So in this case, 1 mole of water weighs 18.02 grams. And notice in this case, the grams are on the bottom and the moles are on the top. Here we go. And the reason we put grams on the bottom is so they'll cancel those grams and leave us with moles, right? This is what you want, so it goes on top. This is what you got. It goes on the bottom, so it'll cancel out what you got. Okay? Okay, aspirin has a molecular formula of C9H8O4. What's the mass of 1 mole of aspirin? That should be fairly easy. You got your formula. They didn't even make you look it up. C9H8O4, right? Okay, so you need, excuse me, you need 9 carbons, right? You need 8 hydrogens, and you need 4 oxygens. And add them up. And that's the molar mass of that formula. Now, is that a molecule? I'm going back a chapter or two. Is that a molecule or an ionic matrix? It's a molecule. These are all nonmetals. So this is a covalently bound compound. That unit acts as a single unit. It's a molecule. Be sure and sign in, or have you already signed in? Yeah, and grab a lab if you don't have a copy already. Okay, so if we do that calculation, we should get 180 grams. So what does that mean? That means 1 mole, 6.022 times 10 to the 23rd of these units will have that mass. Okay? Okay, when we look at a chemical formula, this is just really a reminder. When we look at a chemical formula, we can look at it in microscopic terms or macroscopic terms. All right, microscopic term says that this formula, dinitrogen tetroxide, has 2 nitrogen atoms and 4 oxygen atoms. Okay, that's the microscopic view. But it's more important for us as chemists, temporarily, right? To consider it as in the macroscopic view. That is, if we have enough of those molecules that we can actually measure their mass. But if we only have 1 molecule, it's going to be almost impossible for us, for the average chemist, to measure the mass. So we need a mole of them. So if we have a mole of them, that means that if we have 1 mole of that unit, O4. If we have 1 mole of that, how many moles of nitrogen does that represent? 2 moles of nitrogen and 4 moles of oxygen. Okay? 1 mole of that unit, and you've got 2 of these, 4 of those. Okay. How many moles of carbon atoms and hydrogen atoms are present in 2.5 mole sample of ethane? How would you approach that one? Well, if you have 2.5 moles of this molecule of ethane, how many moles of carbon do you have? 2 times that, right? So you have 5 moles of carbon, and 6 times that is 15, right? Hydrogen. I multiplied 6 times 2.5. If you get this one right, say 2 times 2.5, then what's the ratio? 2 to 6 is 1 to 3. So you have 3 times as much hydrogen. 3 times 5 is 15. Right? There's always more than one way to solve a problem. Let's see. Oh, there's the calculation. Stop me if you have questions. Okay, here's that formula again of what? That was aspirin, wasn't it? How many moles of carbon atoms, hydrogen atoms, and oxygen atoms are present? Well, 9, 8, and 4, right? Yep. Now, I don't know why I leave this one in here. Sometimes it's just confusing to see that type of flow chart. But if you want to take time and study that flow chart, fine. Otherwise, ignore the slide. What I'm going to show you later how to do things, you probably won't need it. Another way to look at it is to use dimensional analysis, right? What do you have? Where are you headed? And what kind of conversion factors do you need in the middle to get there? That's basically what that flow chart is showing you. All you need to know is how to find the conversion factors to get there. Okay. I take a trip from Beckley to Atlanta occasionally because I've got relatives down there. So I need to know how much is it going to cost. Have we done this one before? No. Okay. So where am I? Well, I'm in Beckley. Where do I want to end up? I want to go to Atlanta. How am I going to get there? I'm going to have to buy very expensive gasoline, right? So this slide was created before the latest inflationary plunge we've taken. So the values that you see here aren't realistic, except for the distance. I need to know how far it is from Atlanta to Beckley, and then I need to know what else to find out how much money I'm going to need. Right. How many miles to the gallon, and how much does gas cost? And we should be able to arrange those in a dimensional analysis format. Cancel what we don't want, leave us with dollars. Right, it's 385 miles, give or take. Atlanta's a big place, so it depends on whether you're on this side of the town or the other side. And there's your target. How many dollars? So 385 miles, we want to end up with dollars. All right, how many gallons of gas is it going to take? Well, let's say you've got a car that'll give you 25 miles a gallon. That's a stretch for my car, but it's okay for some. Especially if you got a 4-cylinder, you might even do better. But that cancels miles and leaves us with gallons. Okay. Now that we've got gallons, we want to cancel gallons and leave us with dollars, right? So you need to substitute something a lot bigger than 280 in here. It's more like, let's see, I passed 359 on the way here.
And where I live, it's 319.
Oh, in another state? Here? Really? Okay. Ooh.
But it's also like in Huntington, I think it's like 350 or something like that. It's so different, but
yeah. Maybe it's cheaper for them to deliver the gas to your area. I got to take a trip on Saturday going south to Charlotte. I'll probably cross the border into Virginia before I buy gas. Anyway, assuming it's 280, then the gallons cancel, the miles cancel, and leaves you with dollars. So when this slide was created, it cost $43 to get down there. $43 to get back. And when I'm in Atlanta, I do a lot of driving, so maybe I'll increase that total by about 50%. So it'd be a little over $100 I need to be sure I've got in my pocket or in my account to get down there and back. Because whenever I'm down there, I have to, if I do nothing else, I have to go downtown and eat chili dogs at the Varsity. If I don't do that, I haven't been to Atlanta. Okay. Which one is closest to the average mass of one atom of carbon? This is kind of a dumb slide. No atom of carbon is going to weigh a gram or a multiple of a gram. So just pure logic, right? Pure logic tells you that it should be this one right here. But you can calculate that. Is it going to do it for us? No. Calculate the number of copper atoms in 63.55 gram sample of copper. This is just a test to see if you know what that mass means. If you think, all right, I've got to convert that many grams to atoms, so how am I going to get there? Well, if you have so many grams and you want to get to atoms, what's your bridge? Well, this is numbers of things and this is mass. So you know that you got to use molar mass in there somewhere, because molar mass is the bridge from mass to numbers. So if we do so many grams here and we have grams on the bottom, moles on the top, then we find molar mass, right? And at that time, you look over here and you say copper's molar mass is 63.55 grams. So you know it has, instantly you know it has 1 mole. That's 1 mole. But if we had a different value there, then we would want to get rid of the moles and leave us with atoms. And then that conversion is, we didn't name that, did we? That's Avogadro's number. Right? If it's not in your book, I don't remember seeing it on the slide. But that number is given. It wasn't determined by Avogadro, but Avogadro's work made that possible. Okay, so that's why it's that many atoms, because it's 1 mole. Okay. Which of the following 100 gram samples contains the greatest number of atoms? So for this one, we've got magnesium, zinc, and silver. And we've got 100 grams of each one. Okay. So if we want to know how many atoms of each one we have, actually, since we're comparing numbers of atoms, we don't have to go all the way to atoms to compare numbers. All we need to do is go to moles. If we can go to moles, that comparison will be the same as atoms, because they're both values for numbers of things. So we're obviously going to need molar mass for each one of these. Right? What's magnesium? Well, you look on your chart. Magnesium is 24.3. See, 24.31 grams per mole. I'm starting to get a little light. And zinc. We just did zinc. No, we did copper. Zinc is 65.38 grams per mole. And silver is what? 107.87. Okay. So a mole of these atoms weighs that much, that much, and that much. All right, think of it this way. If you have exactly the same mass of each one of these, how did you get there? You had to get there because each one of the atoms has a mass of its own. Right? And you multiply by a certain value and you get 100 grams. So if we look at it this way, atomic mass units instead, then one of these weighs that much in atomic mass units. And I think I'm barking up the wrong tree. Forget that. Let's stay with grams because that's grams. Okay. If we have 1 mole of these, we only have that much. Right? So how many moles are we going to need to get to 100 grams? Right? About 4 times that, right? Approximately 4 times that will get us to 100 grams. How about this one? Actually, 2 would be too much, so less than 2 times, right? And this is less than 1 time to get us there. All right, so if this is the number of moles, then which one takes the greatest number of atoms to get there? That one. That's because each atom weighs a lot less than the others. Okay. All right. This one is a little more complicated because you have different masses for each one. But it's not that much more complicated. If we have 107.9 grams of silver, 107.9 grams, and zinc is 70 grams, and magnesium is 21 grams. The way to approach this problem is if you're going to put them in order, number of atoms, what are these values in relation to a mole of those elements? Silver is 107.9 grams. So this is equal to 1 mole, isn't it? How about this one? Zinc. If we say we have 70 grams of zinc, 65.38 grams per mole, this is greater than a mole. And that's less than a mole, isn't it? This would have been 24. Now we can put them in order for a descending number of atoms. All right, so the greatest number is zinc. So that's number 1. Then this is number 2, and this is number 3. You want to put them in order. Okay. Now, if that wasn't bad enough, what about this one? We have a 100-gram sample of each of the following. Water, N2O, dinitrogen monoxide, or nitrous oxide, laughing gas, C3H6O2. You probably wouldn't recognize that one. That's probably propionic acid, which is neither here nor there for you, because you need to come back and take organic chemistry to get that one. CO2, carbon dioxide. Okay, so you got those 4, and you got 100 grams each one. Rank them in descending order of number of oxygen atoms. So here's how you would work that. I'm going to invoke Henry Ford, raise him from the dead so he can do this problem for me. I set up an assembly line because each calculation is going to be the same. You just change the conversion factor slightly for each of the compounds. So if we've got water and nitrous oxide and propionic acid and carbon dioxide, we've got 100 grams of each one. Okay. This is a dimensional analysis problem. So if we're going to compare numbers of things, we're going to have molar mass in there somewhere to bridge the gap between mass and numbers, mass and moles. So that's the first place we start. All right, grams on the bottom of each one, because this is in the numerator, and moles on the top. Okay, it's my assembly line. Now I need to put a different value in here for each one. If we take water, 2 hydrogens is 2 times 1.01 or 2.02, and oxygen, 1 oxygen is 16, so it's 18.02 grams. Okay, N2O. Nitrogen is 14.01, so that's 28.02 plus 16. My mind's starting to get a little fuzzy. 28.02 plus 16 is 44.02. Okay, C3H6O2. So we need 3 times 12.01, 6 times 1.01, and 2 times 16. 12.01 times 3, and then 6.06 for hydrogen, and then 32 for oxygen, right? 2 times 16. 74.09. Okay, and then CO2. Carbon is 12.01. Oh, we got one of them. And we got 2 oxygens, which is 32. 44.01. Okay, so now we've changed the mass to moles. Descending number of oxygen atoms. We don't have to go all the way to numbers of atoms, because once we get to moles, that's a unit of measure for numbers. If we're just going to put them in order, but we're not finished yet, because it says number of oxygen atoms. What does this tell us? This is the number of moles of each of these units, isn't it? So this one has, this is the number of moles of molecules. So what we need is, for each molecule, how many oxygen atoms do we have? Right? In this one, we only have one oxygen. This one, we have 1 oxygen. This, we have 2 oxygens. And this, we have 2 oxygens. Now we cancel the moles of molecules, and now we have moles of oxygen atoms. That's the thinking part. The rest is number crunch. So we divide 1802 into 100 times 1, and it's a value. And same thing for each one of them, and then you compare your values. And in the interest of time, oh, I didn't know I had this slide. I went to all that trouble, and there it was right there on the slide. Okay, so we have 5.56 moles of oxygen, 2.27 for nitrous oxide, 270 for propionic acid, and 455 for carbon dioxide. So put them in descending order. This one has the most. The next most, 1, 2, 3, 4. The least is laughing gas. And you can't just stare at the problem for 5 minutes and then write the answer down on a test. You got to actually do the calculations.
Are you going to give us the periodic table?
Yeah, let me check to be sure, but I'm pretty sure I put it at the end of the test. Yeah, there it is. So you don't have to squint to try to read that. Yeah, it's in the back of the test. I've also got the polyatomic ions, that table. That's it. Okay. Oh, I messed up my animation. That was supposed to come later. Let's see. This formula right here. So what we're going to do is we're going to take 0.325 gram sample of aspirin, which is 325 milligrams. Standard dose for an aspirin is 325 milligrams. And ask the number of molecules that represents. Right, so we have that. We're going to go from mass to numbers. That means we need molar mass. And there it is. So we're going to convert. That's the molar mass. We calculated that one earlier for aspirin. We're going to convert to moles. Oh, he wants to know molecules. Okay, so we do have to go all the way now. So there's Avogadro's number to cancel moles and leave us with molecules. And that's how many molecules you have in standard aspirin. See, baby aspirins are what, 81 milligrams, I think. Yeah. So you could do the same thing with baby aspirin. But it has to be grams. Notice that the units have to match, right? If we had said 325 milligrams, you'd have to convert it to grams before you could use this. Oops. That over here. There we go. Okay. Now for chemical reactions. Now that we know how to make those conversions, we know how to write compounds, we know how to determine their molar masses. Now, in order to do real chemistry and know what we start with and what we end up with, we need balanced equations. We need to know what are the reactants, what are the products, and then balance the equation. And when I say balance, I'm talking about Lavoisier's conservation of mass. We covered that earlier, didn't we? Lavoisier said that in a chemical reaction, the mass of the reactants equals the mass of the products. You can't create matter, you can't destroy it. It has to balance. As long as you account for everything that goes in and everything that comes out of a reaction, they will be exactly the same. Now, it wasn't until Dalton came along and with his atomic theory that he was able to explain why that is. And Dalton's explanation tells us that when we have an equation like this, calcium sulfide plus water yields calcium oxide plus hydrogen sulfide. That the way to balance that is to make sure you have the same number of atoms of each element on either side of the equation. So if you have one calcium on the left, you need a calcium on the right. That one's good, right? So far. You have one sulfur on the left, you got one sulfur on the right. You got two hydrogens on the left, you got two hydrogens on the right, one oxygen on the left, one oxygen on the right. That equation is balanced as written. We don't have to do anything to it. Occasionally that happens. But the reactants are always written on the left-hand side with an arrow in between pointing to the right, and then the products are written on the right-hand side. 99 times out of 100, you will have to be given at least the names of the reactants and the names of the products, right? Because the products that come out of a reaction are heavily dependent upon the reaction conditions. So unless you're a chemical engineer, you've got no way of predicting that. There's one type of reaction where you can predict the products. And I don't think we've talked about that yet. Double replacement reaction. Have we talked about that? No. We're going to do a lab. Let's see. Detecting signs of a chemical reaction. That's the next lab, where we actually do a double replacement reaction. One of the choices that we have. We'll talk about that later. But most often you'll be given reactants and products, and then all you'll have to do is be sure that you write the compounds, if any, correctly, or the elements correctly. Suppose we have one of the diatomic elements in there. It says hydrogen reacts with oxygen to yield water. Where are we going with that one? You're going nowhere with that one. It will never balance unless you do this. Right? That's why you need to know the diatomics. Because if the word problem says hydrogen plus oxygen yields water, you need to know that hydrogen is diatomic, oxygen is diatomic. Now, is that one balanced? Nope. You get 2 oxygens here and 1 there. So we have to balance. So how do you balance a chemical equation? Once you've written the elements and the compounds correctly and put them in their place as reactants or products, you can't touch those subscripts, right? They are sacred. The only way you can balance it from now on is to use coefficients, numbers in front. Okay? You can just say, how many of those can I have? How many of these can I have? Right? Once you write that subscript in there, it's chiseled in stone. Okay, so in this case, we need 2 oxygens on this side. But now we have 4 hydrogens, so we need 2 here to give us 4 hydrogens, right? 2 times 2 is 4. 2 times 2 is 4. 2 times 1 is 0, is 2. And there's 2. So that was balanced. That was easy to balance that. Not as easy as that one, but almost as easy. Now, when we get to some that are more complicated, I'm going to give you a method. It's coming up pretty quick. So this explains what the equation coefficients mean. And it's important to recognize that when a reaction occurs, you've got these different elements in here, and you've got these different compounds. But what's really happening is they're just swapping partners. The atoms are swapping partners. And that's as numbers of things are changing places, not masses. That was the problem for chemists in the middle 19th century. I mean, companies were starting to crank out products using some chemical reactions, and a lot of them were in Germany, but some in France, England. And they were doing great as long as the reactions worked, and they were working from recipes. And they were accounting for everything that goes in and everything that comes out in terms of mass only. Right? They had no concept at that time that the reaction is actually numbers of atoms, numbers of molecules. So when something went wrong, they just had to throw their hands up. There's no way they could fix it because they didn't understand what was actually happening in those reactions. So they got together at a college in southern Bavaria called Karlsruhe. This was in 1865. And all the big brains from universities around Europe and all the chemists and chemical engineers from companies came together and said, we're gonna figure this problem out. Well, they were there for a couple of weeks and they just threw up their hands. Said, we don't know what's going on. Fortunately, there was a young chemist there who was also a teacher, and he was a student had been a student of Avogadro. And he remembered something Avogadro taught him. And he did some research of his own and published a paper and he had reprints with him. And he gave a talk at the conference also. And as people were leaving, he was handing out his reprints. So they took those politely, took them back to their companies, to their universities, and some of them read them. And ding, light bulbs went on all over Europe. They said, this solves the problem. What Avogadro had said was, see, they knew masses, but they didn't know numbers. So Avogadro said, if you have two gases that are exactly the same volume, and it doesn't matter what the gases are, you have two gases exactly the same volume, at exactly the same temperature, and exactly the same pressure inside that vessel, then you have exactly the same number of particles in there. And that's my abbreviation N. And whenever you see N without the zero up here, if you see the zero up there, that's a neutron. But if there's no zero, then that means moles, the number of moles. That means under these conditions, those two containers have exactly the same number of molecules. Now, if their masses differ, they know why the masses differ, because each one of the particles is a different mass. And now they can compare them. So that's why they had to go to some standard. They started off with oxygen, like I said, then they went to carbon. So you can compare something you know or you fixed as a value against something you don't know, and you can start putting masses and numbers together in terms of their molar masses. Now they can figure out what's going on because they know numbers and not just masses. Okay. That took a little longer than I expected, but it felt right. Okay, so that's what your coefficients do. They tell you how many of each of the elements or compounds, as the case may be, that you have in this reaction. And you change those numbers until you get exactly the same number of atoms of each element on the reactant side and the product side. That's the end goal, to have those equalities. Well, how do we get there? This slide came with a set from the publisher, right? So you can read it if you want. It doesn't help you very much. I mean, it helps a little bit, but I'm going to give you a better way. The next two slides have hints, helpful hints. And rather than read through them, well, maybe we better. What reaction is occurring? Write the unbalanced equation. And then don't change the formulas once they're written. Now, then look at your reactants and products and say, okay, now let's just do one. I think that would work better. Let's go to this has examples of several. I've got one. Here we go. This one is ammonium phosphate plus calcium chloride yields what? Calcium phosphate plus ammonium chloride. This is a double replacement reaction. Let me see. Let me use my pointer so it'll show up on them. Notice that you have A, B, C, D, and then A pairs up with D over here. And then B pairs up with C over here. That's a double replacement reaction. But notice something else. You have polyatomic ions in there. How do we know? Well, a dead giveaway is that parentheses with a subscript on the outside, right? That means it's a polyatomic. if you have polyatomics on both sides of the equation, a polyatomic, and it is not ripped apart in the reaction, you can use that as a balancing unit. So let's do that. There's more to it there, but I think the animation would probably be more difficult to follow than if I just put it on the board. Okay, so ammonium phosphate is written like this. I'm going to leave out the aqueous and the solid for now, just to save room. And then I'm going to leave a little gap in here for my coefficient for the next one. Calcium chloride. And then we have calcium phosphate and ammonium chloride. Okay. Now, first thing you want to do is be sure that you've written these things correctly. Phosphate is a 3- charge. Ammonium is a 1+ charge. So you need 3 of them to balance. Okay, that one's good. Calcium is a 2+ charge. Chlorine is a halogen. It's a -1. So you need 2 minuses to balance that 1, 2+. 3 minus, 2+, cross multiply. Take the 2 down here and the 3 down here. Okay, that's how you get that one to balance. And then this one is 1 minus, 1+. You're done. Okay, now that we've written them correctly, you tally how much of each one you start with. So we're going to use the ammonium and the phosphate as balancing units, right? Because they didn't change from one side to the other. So out here on the left, I'm going to write, okay, I need to keep track of my ammonias. I need to keep track of my phosphates. I'm not going to put the charges in there. Need to keep track of my calciums and my chlorines. Okay, so on this side, how many do I have to start with? I have 3 ammonias. I have 1 phosphate, 1 calcium, and 2 chlorines. On this side, I've got 1 ammonia. I've got 2 phosphates, and I've got 3 calciums, and I've got 1 chlorine. That's the beginning of our budget. That's where we start. And you can tell using this method right off that this is not balanced. 3, 1, 1, 2, 1, 3, 2, 1. You know it's not balanced. If you have the same numbers here and here at the end for each one, whatever the case may be, then you can tell instantly that you've balanced the equation. Okay, so what do we do next? Well, here's kind of the intuition part. Where do you start first? You can start at the top, right? If you don't know where to start, just start at the top. It may take you more steps than if you have some experience and know where to start at a better place. But eventually, if you've written these correctly, set up your budget, and start at the top, you'll eventually get to a balanced equation. Okay? So, we could do it that way. We got 3 ammonias on that side, and we need 3 on this side, right? So there's your coefficient that says 3 ammonias. So that makes this one 3, but it also changed the chlorine. So now we have 3 chlorines down here. Okay? So this one's good. What else do we need to do? Well, how about phosphate? Now let's skip to calcium. Why? Because if I do phosphate on that side, I'm changing the ammonia again. So I'm going to skip down here to calcium. I need 3 calciums on this side. Right? So that means 3 here and 6 chlorines. Okay? Now I can go back to phosphate. Or I can go to chlorine. It doesn't matter. I got 6 chlorines over there. If I want 6 chlorines over here, how do I get 6 chlorines? I change this, don't I? 6 chlorines, and 6 ammonias. Okay, now I need 6 ammonias on that side. 2 times 3 is 6. But I've also got 2 phosphates now. We're balanced, aren't we? Okay. And the other rule is that we want the simplest whole number ratio of coefficients. So if this had come out to say, if I'd gone through there and just wildly changed numbers and I eventually got it balanced, but I ended up with 4 here, 6 there, 2 there, and 12 there, I would divide the whole thing through by 2 and simplify it. Right? Once you get it balanced, the ratio of this one to that one to that one to that one is fixed. That's a balanced equation. But we want to simplify it. And don't forget, we don't write it, but there's a 1 there. Right? So if a test question pops up and says, what are the coefficients in order for the balanced equation of this one? It'd be 2, 3, 1, and 6. Okay? That's come back and slap many a student in the face. But we can't simplify that any further. So that's the simplest way. And this that I've set up here just to see, probably just to see if I could do it. Animations, right? We did our tallies. And then for this one, I did calcium first, right? Instead of ammonia, I did calcium first. And I've got those little red numbers up there, right here, to show you what order the steps were in. Okay. So that's my budget method. We'll do another one in a minute or two. I think I've got time. I hope I got time. I don't want to eat up your lab time. This one, if we balance this one, let's see. That's the simplest whole number ratio. But notice, others are possible. Oops. I guess I'm not going to show them to you. If you take these coefficients and divide them by 2, right, then you get 1 there, 2.5 there, 1 there, and 1/2 there. So technically that's correct. Or if you multiply by 2, you get 4, 10, 2, and 2. No, that's not right. That won't work. So this one could be a balanced equation, but it's not whole numbers. This is the best answer right here. Which of the following is true concerning balanced chemical equations? There may be more than one. The number of molecules is conserved. Is that true? No. You don't conserve the number of molecules. You conserve the number of atoms of each element. Molecules could be anything, whatever it takes. The coefficients tell you how much of each substance you have. That's a little misleading. When we say how much, we usually mean mass, right? And they don't tell you mass. They only tell you numbers of molecules or numbers of atoms, as the case may be. Atoms are neither created nor destroyed. That is true. You can't create atoms, you can't destroy atoms in a chemical reaction. You need a nuclear reactor to do that kind of stuff. So that one's true. Coefficients indicate the mass ratios of the substance uses. Nope. Mole ratios. Mole ratios are attributed to coefficients. The sums of the coefficients on the reactant side equals the sum of the coefficients on the product side? Nope. It could be anything. It could be wildly different, depending on the molecules that are entering into the reaction. Okay, so that middle one was the only one that was true. Sodium bicarbonate, heat up sodium bicarbonate, you get sodium carbonate, carbon dioxide, and water. So if we balance that equation, it takes two, let's see, it takes two sodium bicarbonate molecules, or formula units, right? That's not really a molecule. It's a formula unit because you've got a metal and a polyatomic. That's the simplest ratio of those two. 1 plus, 1 minus. But two of those units will decompose into one of these units, sodium carbonate, and 1 carbon dioxide and 1 water. Let me see. Okay, that one's balanced, but let me show you how we got there. Iron plus oxygen yields Fe2O3. Now, if we use our budget method, we will put an iron here, an oxygen there, and that's all you need. Right? That's just iron, oxygen, and then you tally them up. So 1 iron, 2 oxygens, and on this side you have 2 irons and 3 oxygens. Okay, one of the hints that I give you on those slides is if you have a single element on one side or the other, save it to last. Why? Because when you put a coefficient in front of that, you only change that one. Or coefficient in front of that one, you only change that one. Put a coefficient in front of this one, you change both the iron and the oxygen. But there's also another hint in one of those previous slides. I think there were 2 slides of hints, maybe 3. Notice that oxygen here is by itself, and over here it's in this compound. This oxygen has a 2 subscript, and that one has a 3. A quick way to get to the end point here is to say, all right, we're going to say, put the 3 over here and the 2 over there. Cross multiply, like we do sometimes. So if we do that, if we put a 3 over here and a 2 over there, what does that do to our balance? Well, it doesn't change the iron on this side, but it makes 6 oxygens here, and it makes 6 oxygens here, right? Otherwise, there's no way that you can get an odd and an even to come out together by just one number. So we do both of them. Now that we've got that taken care of, we need 2 iron. We need actually 4 irons, right? 2 times 2 is 4. So now this iron sitting out here by itself can have a 4. And we're balanced. That's the quickest way to get that one done. So what that means is 4 atoms of iron on the microscopic level, 4 atoms of iron, 3 molecules of diatomic oxygen react together and produce 2 formula units of, let's see, what is that? Iron oxide. Let's see, this is -2, so that's -6. And this is 2, which needs to be a +6, +3 for that one. Okay. Everybody see how I got that? 3 times -2 is -6. All right, we've got to balance that. And we don't know the charge here yet, but we know that the total has to be +6. So we've got 2 irons. That means each one has to be +3. So now we can say iron 3 oxide is that compound. Okay. There's one hint, one trick I hadn't shown you yet. I'm not sure if I'm going to have one example of it. Oh, when you have this balanced equation, you can generate conversion factors from the coefficients. So I shouldn't have erased that. We had 4 irons, 3 oxygens, correct? And 2 iron 3 oxides. There we go. What this is saying is, if you have 4 moles of iron, 3 moles of O2 are required to produce 2 moles of Fe2O3. So the ratio is established. And you can say the ratio of this one to this one would be 4 iron. I should say, these also mean moles. 4 moles of iron for every 3 moles of O2. And that's equal to 1. Because they're equivalent in some form or fashion. It takes that many, and this is the exact number of those that have to go with it. So that's your conversion factor. If you say, all right, I have 4 moles, let's make it more interesting. Say 8 moles. Say I'm given 8 moles of iron for this reaction. How many moles of oxygen will it take to consume all of that and produce a product? Well, let's see. We have 8 moles of iron. So we need moles of iron and moles of oxygen. This is where we are. This is where we want to go. This has 3. This has 4. So 4 into 8 is 2, and 2 times 3 is 6. So we need 6 moles of O2. Okay, those are conversion factors. And you can make a conversion factor using the coefficients. So how many do we have here? Possibilities. We have 1 conversion factor there, we have 1 there, and 1 there. So we have 3 conversion factors out of this equation. But if you need to go the other direction, you flip them. So we actually have 6 conversion factors that we can make out of this equation, balanced equation. All right. Let's see. In this equation, what are the correct coefficients in the balanced equation? And what's the correct mole-to-mole relationship? This one might be worth doing. I got a half hour. How many more slides do I have? That's the question. Okay. I think we got time. So let's balance that equation. Okay. C2H6. We saw that one earlier. It's called ethane. C2H6. And we're going to burn it. We're going to combust it in oxygen. All right. And complete combustion always gives us carbon dioxide and water. Okay, set up our budget. So what do we have? We got carbon, hydrogen, oxygen. That's it. So on this side, we have 2 carbons, 6 hydrogens, and 2 oxygens. On this side, we have 1 carbon, 2 hydrogens, and 2 plus 1 is 3 oxygens. So you can probably see there's a problem rearing its ugly head already. Odd, even. We're going to fix it. All right, for this one, I start with carbon. But I do want to hold oxygen till last because it's a single element. If I put a coefficient there, then I don't change anything else. So let's leave that one till last. All right, so we're not going to touch this one yet. Let's do carbon. We need 2 carbons, right? On that side. But that makes 4 oxygens here, plus 1 is 5. So now we've changed oxygens to 5. All right, how about hydrogens now? Well, let's see. We got 6 on that side. We need 6 on this side. 3 times 2 is 6. Okay. Now we've got 3 oxygens plus 4 is 7. Here we go. So we got carbon and hydrogen done. How do we fix oxygen? Right? We got a prime number here and a prime number there. Never the twain shall meet. Here's the trick. Use a fraction as an intermediate step. So we need 7 oxygens on that side. If we put a 7 here, that's 14. If we put a 6 here, that's 12. Put a 5, it's 10. Still not 7. Put a 4, it's 8. Close. Put a 3, it's 6. Right? We jumped right over 7. So 7 halves of O2 is 7 oxygens, right? Any problems, or nobody wants to argue? Look at it this way. You've got an oxygen molecule here, right? That's this one right here. If you have 7 of them, you'd have 14 oxygens, right? What if you take half of that? Just say half of this thing right here times 7. So half of that one, and then times 7. That'll give you, well, half of that would be 1, actually. Half of that would be 1. A whole would be 2. Half would be 1. 1 times 7 is 7. Okay? See, do I see puzzled looks?
7 times 2 is 14, divided by 2 is 7.
Yeah, that works. Okay, so now our equation is balanced, but we got a fraction. We don't like fractions in our equations. So how do you get rid of that fraction? The ratios now are exactly right. 1, 7 halves, 2, 3. Those ratios are a balanced equation. So anything we do to one, we have to do to the others to maintain that ratio. Okay, so we're going to use a mathematical trick. Right? If you have an equation in math, if you multiply the whole equation through by a constant, you still got the same equation, don't you? So we're going to do that with this one. What's the constant, though? We want to get rid of that fraction. So multiply the whole thing through by 2. Then the 2 cancels that 2 and leaves you with 7. All right, so we've got a 7 there, we've got a 2 here, we've got a 4 here, we've got a 6 there. And that 2 is used up. So our coefficients are 2, 7, 4, and 6. Okay? I think that's the only other trick I had in that helpful hints. So with those tricks and that budget method, a great many reactions are now within your reach for balancing. Some, believe me, there are some that are grizzly bears. But if I don't throw them at you, then don't worry about it. Right? That'll get most of them. That'll get actually all of them that I'll throw at you. Let me take just a quick peek here. Are we going to get into redox reactions? We do those yet? Where electrons are transferred? No? Okay. Because there's another trick that you can use with redox reactions. But if we don't have to deal with them, don't worry about it. Okay, so what do we do with stoichiometry? Stoichiometry is a fancy word. I think it's derived from the German. It just means that when you know how much mass of reactants are going in, you can predict how much mass is coming out as products. So you might guess that if you know the mass of a reactant, then before you can do anything with that equation, the balanced equation, you're going to convert it to moles. Because we're talking about numbers of things reacting, not masses. So once you've converted your mass to moles, then you can move in your equation and answer questions. And that's what we're going to do with stoichiometry. I'm going to skip that. You know, I need to do something with this slide. This particular problem is a valid exercise, but it's like you put on your bathing suit, you don't know how to swim yet. Right? So they take you in a room and they draw pictures on the board and says, this is what you're supposed to do when you're in the water, right? And then they take you out to the pool and throw you in the deep end. That's what this does. I've shown you how to balance equations, and then I bring you over here and then throw you in the deep end. Let me see if there's a simpler one on the other side of this. No. Okay, I'm going to try to simplify it enough that the slide won't be completely wasted. We've got two different reactions here. Methane burned in oxygen yields carbon dioxide and water. Right? So if you want to know what's happening here, you got to write the equation. And we've told you what methane is because we haven't named that yet. That's an organic compound. So methane is CH4. Right? We're going to burn it in oxygen and yield carbon dioxide and water. The other reaction is ammonia in oxygen. And that yields nitrogen monoxide plus water. Okay, those two reactions. What this problem says, well, this slide just says balance the equations. This one is fairly simple. We can set up our budget, you know, and if you go home and set up your budget. But this one is really, really simple. You've got a carbon here and a carbon here. You've got 4 hydrogens and 2 hydrogens here. That'll give us 4 hydrogens. And still keep 1 carbon. But now we have 2 plus 2 is 4 oxygens. 4 oxygens. That equation is balanced. You can do the budget and prove it to yourself. This one might take a little bit more work. Let's see. Why don't we do this one budget? N, H, and O. Okay, we've got 1 nitrogen here, 1 over there, and 3 hydrogens, and 2 hydrogens, and 2 oxygens, and 2 oxygens. So which trick does this look like would be amenable? I can see cross multiplying in our future because this hydrogen is 2 here and 3 there. 2 and 3. What if we put a 3 here and a 2 here? Now we've got 6 hydrogens here, and we've got 6 hydrogens here. But now we've got 3, 4 oxygens, right? 1 plus 3 is 4. And over here, we've got, still got 2 oxygens, but we've changed the hydrogens. But we already did that. 2, here we go. There you go. Now, if we put a 2 in front of this one, we fix the nitrogens, but we've messed with the oxygens. So we have 2 plus 3 is 5 oxygens, right? Okay. Quiet. So now how do we get 5 oxygens out of that? Use our fraction, right? Okay. Assuming I did all this right, then we need a 5 halves here. That gives us 5 there. And then we get rid of the fraction. So that leaves 5 there, 4 here, 4 here, 6 there. So our coefficients are 4, 5, 4, and 6. And let's clean this mess up a little bit. 4, 5, 4, and 6. There we go. Now those equations are balanced. That was the first, this slide tells us to do that, balance the equations. And 4, 5, 4, and 6. Okay. I'm happy. Okay. Now the question is, with these balanced equations, what mass of ammonia? What mass of ammonia would produce the same amount of water? The same amount of water as this equation. Exactly the same amount of water as this one if you started with 1 gram of methane. So the connector between these two reactions is the amount of water. So how do we do that? Well, in order to get back over here, we can't go directly from there to there because the reactions aren't really connected except through the question that's asked. So we need to find out how much water is produced from 1 gram of methane combusted with excess oxygen. Once we find out how much water, in fact, we don't even have to find grams. We can find moles, right? Water's water, moles are moles. So if we find moles here, we can say, okay, that many moles here, and then work our way back. One thing about equations is, if you're going to do any stoichiometry, you cannot go anywhere until you have moles. You have to have moles before you can move in this equation because these ratios are 1 mole, 2 moles, 1 mole, 2 moles, not mass. So we've got to convert that to moles. How do you convert grams to moles? Think of it this way. There's several great walls here. There's a wall, there's a wall, there's a wall. You can't get over or under those walls unless you're a mole. I guess if you're a mole, you go under. So we got to convert that to moles. So how do you convert 1 gram of methane to moles? Dimensional analysis. We need to get rid of the grams and leave us with moles, right? So once you see grams and moles in a quotient, think molar mass. What's the molar mass of methane? Well, it's 12.01 for carbon. And 4 hydrogens. 4 times 1.01. 16.05. All right. So 16 into 1, or just take the inverse of it. Let's see, do I have an inverse key here? I do. 6.23 times 10 to the minus 2. 6.23 times 10 to the minus 2 moles of methane. Now you got moles, we can use our ratio because these are mole ratios. If you're going from 1 mole to 2 moles, the ratio is 2 to 1. So if we want to convert this one to moles of water, we need moles of methane on the bottom and moles of water on the top. I left out the mole part. So the coefficient is 2 here and 1 there. So 2 times that value is the number of moles of water produced from the top reaction. 1.25 times 10 to the minus 1. Moles of water. Okay? Now we can move to this equation. We want to know what mass of ammonia will give us that many moles of water. Right? Isn't that what it said? Same amount of water. How much ammonia will produce the same amount of water in this reaction as 1 gram of methane in that reaction. So now that we have this many moles of water, we can back calculate to that one. Okay, so now we know this one. 1.25 times 10 to the minus 1 mole of water. I'm going to put the conversion factor on this side since we're going that direction. So we need water on the bottom, right, to cancel and leave us with ammonia on top. And what's the ratio? 6 and 4. Okay, so 2/3 of that value will give us the moles of ammonia. (8.31 times 10 to the minus 2). 8.31 times 10 to the minus 2 moles of ammonia. Okay, we're almost there. We know how many moles of ammonia will produce the same amount of water. We don't know the grams yet. So what do we do now? We want to get rid of moles. Moles is in the numerator here, denominator there, and grams here. So quotient, molar mass. What's the molar mass of ammonia? Nitrogen is 14.01 and 3 hydrogens, 3.03. 1704. These moles cancel. That number times that number. Let's see. Yeah, they're in my calculator, so I just multiply. 1.42. 1.42 grams of ammonia will produce the same amount of water in this reaction as 1 gram of methane does in that reaction. Okay? That's what I meant by throwing you in the deep end. There's a lot to take in there at one time. All right. So this is the animated version. We found out that much water from this reaction, and then we take that much water and work backwards to find that many grams of ammonia. So the emphasis here is on the fact that in stoichiometry, if you want to know products or reactants, doesn't matter which, starting from someplace, you've got your conversion factors here, but those conversion factors only work if you have moles. So if you're given grams, convert to moles, then you can move. And that's the rule no matter what you've got. in this case, we had mass here, but we could have a solution of a certain concentration and milliliters of the solution. And you could figure out how many moles you have and then work from there. So you're always headed toward moles to get somewhere in an equation. Okay. Percent yield. All right, here's the other fly in the ointment. If you're a chemical engineer, you're working for a company, and your company could make money or it could lose money on a process. What you want to do as an engineer is you want the reaction that you've been given to work with to produce the most product possible from a given amount of reactants. Right? You want a high yield, lots of product for this amount. That puts more money in your company's pocket. If you can't get up to an acceptable level, then they have two choices. You know, they can throw that reaction out and try a different one, or they can fire you and hire somebody else. And sometimes that's what they do. So what does percent yield mean? It just means that when you run that reaction, you determine what is the actual yield. How much mass do I get out of this reaction from a given mass of reactant? How much product do I get? And then you run the reaction. You say, all right, if I have 1 gram of this, I'm going to end up with this many moles of water, and you can convert that to mass. That's the theoretical yield, right? So this balanced equation, if you start off with a value here, you get a theoretical yield, right? That's perfect, 100% conversion. But if you actually run that reaction, you may get less than that, right? And for various reasons. It could be internal to the reaction, right? The conditions just aren't quite right. Or it could be that when you isolate your reaction product from the mixture that comes out of the reactants, right? You have this and you may have 12 other products. It's not 100% efficient. You might lose something in the purification process. But whatever the case may be, once you know the theoretical yield from your balanced equation, and then you actually run the reaction and you get an actual yield, then you just ratio those two together times 100, and that's your percent yield. Most often, it's done with mass because it's convenient. But you can also do it with moles. You can ratio moles, and it gives you a value. So, like I say, with all percent values, you got to know where did that percent come from. Right? Why? Because percent is just parts per 100. It doesn't tell you if it's volume or mass or moles or what. It doesn't say. So when it says percent yield, you need to have some indication in the problem as to where it came from. Did it come from mass? Did it come from moles? Did it come from volume? Right? So that's the bad thing about percent. Percent's a dimensionless number. All right. What would be the percent yield of a product for a chemical reaction where the theoretical yield and the actual yield are 5.6 and 4.5? So the actual yield is 4.5, the theoretical yield is 5.6. You just divide 4.5 by 5.6 times 100. Anybody do that? What'd you get? Right on the button. 80% yield. That's a good yield. That's a really good yield. When Fritz Haber was trying to make ammonia from nitrogen in the air and hydrogen. The best he could get with his process was 15%. It was a stubborn reaction, but that was good enough, you know, for his country, the Germans, during World War I, to make it in sufficient quantities that they could then they could take the ammonia that was produced and oxidize it and make nitrates, and then they could go to gunpowder. So I imagine 15% was good enough because the government was subsidizing it. Okay. Let's see. These are probably the last questions in the bunch, aren't they? Yeah. Did you know that pennies that were produced prior to 1982 were 95% copper? And pennies after that year, well, in 1982 and after, were the proper term in economic circles is the currency was debased. They put zinc in there. They had these zinc size, penny-sized zinc blanks, and they coated them, they cladded them in copper because zinc is a lot cheaper. And they made pennies like that. And nowadays, if you want to get the copper out of them, then you drill a couple of holes in the clad and you drop your penny in hydrochloric acid, and it'll eat up the zinc and leave you with the copper because it won't react with copper. But if you want the zinc, then it takes a little more work. There's a reaction you go through, and it converts the copper outer layer into an oxide, and then you rub it off and you got your zinc. But that's not the question. The question is, these pennies weighed 3.11 grams. And they were 95% copper. How many atoms of copper were present in one pre-1982 penny? Well, not just hint, remember the significant figures, but hint, remember that 3.11 grams is only 95% copper. I think it had zinc mixed into it. That was an alloy. And coins were meant to be used day in and day out, handled, banged around. So you wanted something that was durable, right? So if you made your coin out of copper, copper is a soft metal. You make an alloy out of it. You put something else in there to harden it, make it harder, and it would last longer. They did that with silver coins, right? They were 90% silver before that year, 90% silver and 10% copper. And they would last longer than pure silver, like bullion coins that you can buy today. 99.999% pure. So you would take the 3.11 grams and you would find out how much actual copper is in there. 0.95 times that value, right? 95%. And you would find out how much copper that's actually in there. And then you would convert that. Let's just do it. 3.11 0.95 times 2.955 grams of copper. Then you convert that to numbers of atoms. So how would we do that? You got to go from mass to numbers, right? So you got to have molar mass. So what's copper? 65 something, isn't it? 63. 63.55. 63.55. There we go. So that gives you numbers in moles, and then they want to convert it to moles to atoms. So what's the magic number here? Starts with an A. Avogadro. There we go. So that's the thinking part. We got grams canceled, we got moles canceled. Now all we have to do is say this number divided by that number times that number gives you the answer. Let's see. And there it is. 2.8 times 10 to the 22nd atoms. Now, why did I keep so many significant figures here? If I hadn't told you before, all of these operations are multiply or divide. So we had the same rule working through the whole thing. That means the answer has to be restricted to, that should be more than that, right? That's only two significant figures and you got three here. These are conversion factors, right? That's not conversion factor. That one, that one, that one. So they're exact numbers, right? This is the only one that determines the end product. You can keep as many as you want intermediate as long as the final answer is restricted. Because the operation is multiply divide, you only have one rule, right? Remember, if you introduce add subtract rules in there, then you have to go intermediate and work your way down. But this way, if you keep all your significant figures until the end and then round, you avoid rounding errors at intermediate steps, right? If you got this step, go round up, round up, round up, you're way off by the time you get to the end. So that one should have three significant figures. All right. One last one. We got time? No, we're out of time. Right, 11 o'clock. We need to do the lab. So for posterity, there. I'll leave it up there long enough.